In the next few slides, I'm going to be covering the electronic structure of atoms. And those of you that have done this before in past chemistry, if you have studied chemistry in the past, you will see that I'm going to dwell into it very little because I've only selected things that I think will be useful for your future careers, your future degrees, whether you're an animal scientist or an ecologist, etc. And that means that you don't need to know how to do an electronic configuration of an atom, according to my opinion. What you need to have is a working understanding of how an atom looks like, how the electrons are distributed, how and why atoms use certain electrons and not others. So this is the aim of these slides. So if you know more about the electronic structure of atoms and you want to discuss that with me, that's fantastic. And if not, with what I'm telling you, hopefully will be enough to enable you to continue both in this module and in your future modules in the rest of your degree. So electrons move around the nucleus of an atom at speeds approaching the speed of light. And because they're so small, and the equipment we use to measure them, it provokes changes in what we are measuring. It's impossible to know exactly where an electron is at a specific point of time and how fast it's traveling. And those of you might have come across before the uncertainty principle. So we don't know where an electron is. What we can know is the probability of finding an electron in a particular region of space, and in a particular region of space around the nucleus. And that is what the orbitals tell you. So it's not what the electron is or where it is where it is more likely to be, where the probability of finding that electron is equal around that area of space around the nucleus. So yes, the atomic number defines the element and it tells you how many protons it has and how many electrons it has, but actually it is the arrangement of electrons in an atom that tells you, that is going to determine how that atom is going to interact with other atoms, how it's going to react. And specifically, we care specifically about those electrons that are further away from the nucleus, because those are the ones that are going to be used to make bonds. So when you talk about the structure of an atom, the electronic structure of an atom, we talk about energy levels. And we talk about energy levels because electrons in an atom do not circulate freely. They actually circulate in very specific, they are restrained to specific areas of space, to specific energy levels. We say that energy in an atom is quantized. And what we are looking at these are quantum numbers. So the energy quantum number is given the letter n, and it starts with 1, closest to the nucleus. 2, 3, 4, 5, 6, 7 is the max. In theory, you can have as many as you want. In practice, the periodic table stops at energy level 7. And the higher the number, the further away, the higher in energy they are, and the further away they are from the nucleus. So more likely to react. We care specifically about the furthest away electrons, the ones that are further away from the nucleus. And we call that the valence shell. And we're all about the valence shell in chemistry. It's all about how many electrons you have there, how far are they from the nucleus, and how interested they might be with interacting with another nucleus of another atom. Within those energy levels, electrons are actually in as much as you don't know where they are in specific regions of space. And we define something called orbitals. And orbitals are locations, they are solutions, mathematical solutions of the Schrödinger equation. And it specifies the location where there is a high probability of finding a particular electron. We call those atomic orbitals, and those of you that have done chemistry before will have heard about s, p, d, f orbitals. So those they are. They don't tell you where the electron is, it tells you there's an equal and high probability of finding the electron in that particular area. So these subshells, those differ in energy. The higher energy, the larger the subshell is, and the more electrons it's going to be able to accommodate, because you will see that you have more than one type of orbitals that belong to that subshell. So Each orbital will only be able to accommodate with inverted commas 2 electrons, but you only have one subshell S, you have 3 subshells P, you have 5 subshells D, and 7 subshells F. And that's why a subshell S can accommodate 2 electrons, a P6, a D10, and an F14. So again, those are regions of space within a particular energy level that contain electrons that have the same energy. And as you move from S, P, D, and F, you have a slight increased energy within that particular level. So when you are in energy level 1, you're the closest you can be. Those electrons are the closest they can be from the nucleus, and you have S-type orbitals. S orbitals are spherical, and they surround the nucleus. And in this case, because you are in energy level 1, you call this orbital 1s. S because it's an S-type orbital, and 1 because it's an energy level 1, the closest to the nucleus. In energy level 2, you move slightly further away from the nucleus with respect to 1. You have 2 types of orbitals, 2 types of subshells. You have the spherical ones, the S, one of them that you had before, but in this case it's a 2s because you're in energy level 2, and you have 3 p orbitals, and p orbitals have this sort of dumbbell shapes, and they are pointing towards the different sides of space, the x, y, and z axis, the different axes. And so they orient alongside the x, y, and z axis, and that's what we call them px, py, and pz. And the 2 denotes that you are in energy level 2. When you're in energy level 3, again, you're slightly further away from the nucleus, slightly higher in energy. You have 3 types of subshells, 3 types of orbitals. You can have the S ones, but this will be 3s because you're in energy level 3. You have the p orbitals, and they will be 3p. And you have the d orbitals, and the d orbitals, there are 5 of them, and as you can see, they have quite an interesting shapes. And again, the x, the y, and the z denotes whereabouts they are with respect to the 3 axes, x, y, and z. Energy level 4, again, slightly further away from the nucleus, and and you have slightly higher in energy. You have 4 types of sublevel. We have 4 types of orbitals: the S, the 3p orbitals, the 5d orbitals, and you have a new types of orbitals, the F type, and there are 7 of them. And I haven't there, you will see if you go to this webpage, which I will encourage you to go. I haven't there to draw them because they are quite complicated. They are mathematical equations, and they get more complicated. Sorry, they are functions, and they're representations of 3D representations of the solutions to Schrödinger equation, and they get more complicated as you add as the orbitals progress. But you can go to that webpage, and I would really encourage you to go to that particular webpage from the University of Sheffield, because it shows you the different orbitals, S, P, D, and F. It shows you also proposed orbitals. I haven't seen them yet, but they have been, it could be proposed that if we have elements with enough electrons, you would see them, G, H, and I. And it also shows you the difference between a 1s orbital and a 2s orbital. You will see they are larger, so they have the same shape, but the size changes as you move further and further away from the nucleus. So it's a really, I would really recommend you to go to this website from the University of Sheffield. So subsequent energy levels, 5 to 7, repeat the subshells. So you have S, P, D, and F, just at higher energy levels. So instead of being a 4s, it's a 5s. Instead of being 4p is a 6p or a 7p. So an electronic configuration is a statement of how many electrons an atom has, and specifically how many electrons an atom has on each particular subshell. And if you have a tiny atom like hydrogen that only has 1 electron, you will only have 1 energy level and 1 subshell, because if you have 1 electron, it can be only in a 1s orbital, as close as possible to the nucleus. And if you have an atom like helium that has 2 electrons, then yes, again, they can only be as close as possible to the nucleus, and they will be a 1s orbital. And if you have something like uranium that is 90, it has a 92 electrons, then you have many energy levels, you have all subshells, sp,d, etc. So depending on the number of electrons your atom, your element, the element you're looking at has, you will have more or less of those energy levels and those subshells filled. And if you have ever done electronic configuration, or if you like to practice them, please let me know, because you can have a go at them. But this is not something I'm going to cover in this module, because I think that what is interesting is not something that is going to be useful for you for the future. So the only thing I want you to keep in mind is that electrons in the electronic cloud, they are not just randomly distributed, their energy is quantized. They can only occupy specific regions of space. And we come up with these energy levels, and energy levels tells you how close those electrons are to the nucleus. And we come up with those orbitals, these shells in energy, and that tells subshells, and that tells you the probability, the areas of space around the nucleus where electrons have equal probability to appear. And they have different shapes depending on the different solutions of the Schrödinger equation. When atoms react, they react to try to fill these outer energy levels to reach a more stable state, and the aim of the atom is to try to stop reacting. So it keeps reacting until it tries to find an electronic configuration of all those electrons that is as stable as possible. So by sharing, exchanging electrons, by making bonds, atoms have tried to fill those outer energy levels in an attempt to achieve a more stable state. And that's what reactivity comes about. That's how reactivity comes about.